Hi, so in this video we're going to be looking at modelling with volumes of revolution. So when we model real life problems with a volume of revolution, this often involves similar shapes and the volume scale factor. So in this example, we're told that a scale model of a fruit ball is modelled as a solid of revolution of curve C about the y-axis. And I want to show you what this will look like as it is rotated around the y-axis. So we have this function, and as we rotate the curve around the y-axis, you can see that we create something that looks like a fruit ball. And it's the volume of this fruit ball which we're going to find, or this model that we're going to find, okay? And we're told that the curve C has parametric equations, x equals 4t and y equals 2t squared, where t is between negative root 2 and positive root 2, and the units of x and y are in centimetres. So for part A, we've been asked to work out the volume of a fruit ball, given our answer the multiple of pi. So there's two ways that we could attempt this. We could use the Cartesian model, where the volume is equal to pi times the integral in the limits of y1 and y2 of x squared dy, or we can use the parametric model, where we have a volume is equal to pi times the limits now in terms of t, so t1 and t2, of x squared, and this time dy by dt, integrated with respect to t. So we could use either of these two models, and depending on which model we used, our approach would be slightly different. But because we've got fairly simple parametric equations, it should be quite easy to find the x squared here from each of these. So we're given that y is equal to 2t squared, so therefore t will equal, we'll move this over to here and then we'll take the square root, so t will be y over 2 square rooted, and then we'll substitute this t into this t to work out x. So we have x will equal 4 lots of t, which is the square root of y over 2. We'll move this 4 to the left hand side and square both sides, so we get x squared over 16 will equal y over 2. And then to get x squared, we'll multiply both sides by 16. So x squared will equal 8y. So we have this x squared here, but the next thing we need to do is to work out our limits. Well, we can see the first limit is when y equals 0, but now we need to work out our upper limit. But our upper limit for y will be from this value of t, which is root 2. So all we need to do is substitute this root 2 into here. So y will equal 2 lots of root 2 squared, which will equal 2 times 2, so y will equal 4. So we have our limits, and we have the x squared. So now we can work out our volume. So the volume will be pi times the integral between 0 to 4 of x squared, which is 8y, integrated with respect to y. And because this is a constant, I can move this out in front of our integral sign. So this will give us 8 pi times the integral between 0 to 4 of y, dy. So now we'll integrate the y, and we get 1/2 of y squared between the limits of 0 to 4. And now we'll substitute in our limits, and we get 8 pi times 1/2 of y squared is 1/2 of 16, so this will be 8. And then substitute in the 0, and we get 0. So the volume will be equal to 64 pi centimeters cubed. Okay, so for part B, we're told that the real fruit ball has a volume of 1,728 pi centimeters cubed. Find the height of a real fruit ball. So now we're looking at similar shapes. So the volume of the real fruit ball is 1,728 pi. If we divide this by the volume of a model, which is 64 pi, then we get our volume scale factor. And this works out as 27. These two pi's will cancel. So now we can work out the length scale factor, which will be the square root of a volume scale factor. So the square root of 27 will equal 3. So the height of our fruit ball, well, we know that the maximum height of our fruit ball and our model is 4. So this will be 4, the height of a model, multiplied by the length scale factor. So this will give us a maximum height of a real fruit ball of 12 centimeters. Okay? Well, thank you very much for watching. I hope you found that useful. You can download a full lesson and worksheet from my website, mrmathematics.com. There's a link in the description below. Thanks again and take care.